Okay, this is going to be the fourth video on how to find the interval of convergence of a power series. And if you haven't done it yet, I would watch the first three videos, and it'll give you a little bit of an idea of kind of what some of these steps are like. Now, again, when you're trying to find the interval of convergence on a power series, the idea is that for some values of x, the series will converge, and for other values of x, the series will diverge. So you want to use the ratio test, as we've talked about in the previous videos, to try to identify what values of x will make the series converge. And before we get to the actual problem, let's take a quick look at the ratio test, just to remind you of what that is. So again, what the ratio test says is this. If you have a series that has non-zero terms, if you find this limit and that limit is less than 1, you can show that the series converges. If the limit's greater than 1, you can show that it diverges. And finally, if the limit was equal to 1, then the ratio test failed and you had to use another test. But again, in the interval test, or the test for convergence, we're going to primarily look at this top one up here. We want to know where is the limit, and we're going to concentrate on this. Where is the limit less than 1? Because where the limit is less than 1, then you'll know that the series converges. So that's just a quick review of the ratio test. Now again, if you're not familiar with the ratio test, you might want to back up and watch the ratio test videos before you do this, just to remind you of how to do that. So back to our problem. Now again, in this case, before we get started, just what will happen is this. It could be something like x minus 3 to the n power, or it could just be x to the n power. Now, since this is just an x, that tells you that this series is centered at 0. It's centered at x is equal to 0, because there's no minus. Usually it's in the form x minus c. So we know that it's centered at x is equal to 0. Now again, to use this test, and we'll scoot down here just a little bit, in the first couple of videos we did this. In the first video, we found the limit of the ratio test, and remember, whenever you find the limit, there's only 3 possible outcomes on these things. If the limit's equal to 0, the limit could be equal to infinity, or the limit could be equal to a fixed number. In the first video, the limit was equal to 0, which means that the radius of convergence was infinity, and the series converged for all values of x. In the second video, the limit was equal to infinity, which means that the radius of convergence is 0, and the series only converged at the single point x was equal to c. Then in the third video, we found the limit was equal to some fixed number, which means that there was a definite interval of convergence. We had some fixed distance r and found the interval in which it converged. And then finally, remember, in this last case, if it turns out to be a fixed interval, you have to include a final step, which we will scoot down here and see, and it says, so if you have a fixed interval, the ratio test always fails at the endpoints of the interval, so you have to test each endpoint separately using what I would call any appropriate test. So just keep those in mind as we go through this. So now we'll go ahead and work this problem, and we'll do it the same way, and specifically I want to emphasize this. This is the first problem where we've actually had a minus 1 to the n, and sometimes this term right here causes students some confusion. So in this video, we'll specifically concentrate on how you can eliminate that and why it shouldn't be a problem for you. Okay, off to the ratio test. And what it says is this. It's the limit. Now, in the denominator, you just put the original series. In the numerator, you put the original series with each n changed to an n plus 1. So I would start by just writing down the denominator, which is going to be the original series. So what that's going to look like would be this. I'll have minus 1 to the n power times x to the n divided by n plus 2. Then in the numerator, just everywhere you've got an n, replace it with an n plus 1. So this is going to be minus 1 raised to the n plus 1. Then I'll have x raised to the n plus 1. And then divided by, and again, I'll put it in parentheses, but replace that n with an n plus 1. So I'll have an n plus 1, then plus 2. So when you set it up, it's going to look like that. Well, now the next step is always change it from a division problem to a multiplication problem. So we'll change this into the limit as n approaches infinity of the absolute value. And I'll go ahead and put this across like this. And again, it's just this thing, which is minus 1 to the n plus 1 times x to the n plus 1. Now, on this one, I'll do this. I've got n plus 1 plus 2. I'll put that together and make that just be n plus 3. then times, now again, you've got a fraction divided by a fraction, so invert the denominator and change it into a multiplication problem. So this is going to become n plus 2 divided by minus 1 to the n times x to the n. And then here's the absolute value sign. Now, one of the things that causes some trouble is this, how do you handle this minus 1 to the n thing? And the logic goes something like this. All this can be is either a negative 1 or a positive 1. All this can be is either a negative 1 or a positive 1. So it can only be a 1 or a negative 1. But because of these two absolute value signs here, when you take the absolute value signs of it, it's always going to turn into a positive 1. So the end result is this little negative 1 here will always become a positive 1. So in effect, you can eliminate it. Just replace them with a 1 if you want to, because again, when you take the absolute values, it'll always turn into a positive 1. So basically, just forget about those two because of those absolute value signs. Now, the next thing you can do is this. I want to make things cancel out, so I'm going to take this just like we've done in previous videos. I've got an x to the n down here. I'd like to get an x to the n up here, so I'm going to take this term and rewrite it as x to the n times x to the first power, because that's what this is. And I can replace this with this. And the reason I do that is because now I can cancel out those two x to the n's. So we'll go down and continue on. So that gives me the limit as n approaches infinity of the absolute value of, now in the numerator, I can do this. I'll do them in red here. Well, we'll go ahead and just cancel these out. So in the numerator, I've got an x to the n. The denominator, I've got an x to the n. This x to the n will cancel out this x to the n. And the only thing that's left in the numerator, I'll have this x, and I'll have this n plus 2. So I've got an n plus 2 here. Then in the denominator, I've got an n plus 3, and when it simplifies, it turns into that. Now I want to find the limit of that, so the limit as n approaches infinity, and I'm going to use the same trick that we used before in a couple of problems. Again, when you find the limit of this, n is the variable. You can treat x as if it's a constant. And whenever you're trying the limit of a constant times something, you can bring the constant to the outside. So I think it's always easy if you take the x term and move it to the outside, which is what I'm going to do in this step. I'll rewrite this as, this is going to become n plus 2 over n plus 3, and I've got the absolute value of that. And again, I'm going to take the constant and move it to the outside. Doesn't really change anything, but this is going to become the absolute value of x. Now, by doing that, all that does, it makes it a little bit easier, I think, to find this limit. So now the limit only has n's in it, and I don't have to worry about this x. So you can always take the x part and move it to the outside. Okay, so now it's just a matter of finding this limit. So what this is going to be, and again, you can find this limit. You've got a polynomial on the top, polynomial on the bottom. The coefficient here is 1. The coefficient here is 1. Both these are to the same power. So you might remember from your limit rules, if the exponent on the top is the same as the exponent on the bottom, then the limit is just the ratio of these two terms right here. So this entire thing will turn into 1. So that limit is going to be 1, but you've still got this times the absolute value of x out here. And that's going to be the limit. So now you found the limit. So now by the ratio test, you want to know for what values of x is this thing less than 1. So always put a less than 1 here. And again, I like to add a little question mark just to remind me of that's what I want to test. So I want to know where's the absolute value of this less than 1. Well, again, that's like having the absolute value of x is less than 1. And whenever you have an absolute value, you can always write it as, here's the x. It has to be less than the positive value, and it has to be greater than the negative value. So you can change this into this. Now what this does, this actually gives you an interval, and we'll just draw a picture of it right here, where it converges. So if I draw a number line, say it looks like this, on that line I've got the following. It's centered at 0. It goes over to a positive 1. Now at this point it's an open interval at 1. Here is an open interval at negative 1. the radius of convergence, so r would be equal to 1. Going this way, r, the radius of convergence is 1. So that's what you know right now. Now again, because this had a fixed interval of convergence, you know that the series will converge for any x that's inside that interval. But what you're not sure about, and we'll put a little question mark here, you're not sure about what happens at the left endpoint and what happens at the right endpoint. Now remember, the ratio test always fails at the endpoints of an interval, so you have to test each one of these separately, and that's what brings us to our separate rule right here. So let's do this real quick. We'll scoot this thing up. We've got a little more room to work with. And we're going to go to the second step. Now what the second step says is this, if it fails, you must test it, each one separately. So you go back to the original problem, and in this case, the original problem was the summation. We'll write it like this, the summation, and actually I'm going to test the left endpoint first. So I'll test the left endpoint. So the left endpoint. And what that's going to be would be the summation as n equals 0 to infinity of, and the original problem was this, it was minus 1 to the n times x to the n divided by n plus 2. So when you test it at the left endpoint, all you do is replace x with the value of the left endpoint, which is negative 1. So that's going to turn into this, from n equals 0 to infinity, and you've still got this negative 1 to the n divided by, and you're going to plug in a negative 1 right here to the n, and you've still got the n plus 2 in the bottom. Okay, now what these do, okay, so this is going to be equal to the summation of, from n equals 0 to infinity, of, now in the numerator you can do this. It's going to have a negative 1 to the n, negative 1 to the n. These can only be, both of them will be a positive 1 or both of them will be a negative 1, but in any case when you multiply a negative 1 times a negative 1, it will always wind up being a positive 1 in the numerator. So that's going to give you this. Now this, you may recognize from previous work, you can show that this limit actually diverges, and you'll be doing that using the integral test. So I will show that this thing diverges, and we won't run through the whole thing here, but this will be diverging, and justification from this would be using the integral test. Now you may have to back up and review the integral test to find out exactly how to do that, but in this video we're just going to concentrate strictly on the interval of convergence. So if this thing diverges, remember if it diverges, that means that you do not include the endpoint. So do not include the endpoint, which means that this left endpoint is going to be open. So now we'll test the right endpoint. So we'll go down here to the right endpoint. So when you test the right endpoint, just starting with the same formula, but this time plug in a positive 1 for x. So this would be equal to the summation from n equals 0 to infinity of negative 1 to the n power, and again in place of x, this time plug in a positive 1 to the n, all divided by n plus 2. Now this time it'll look like this. Summation n goes from 0 to infinity, and again, 1 to any power is just 1, so this will wind up being a negative 1 to the n divided by n plus 2. And you want to know, does this series converge or diverge? Now again, sometimes it helps to write them out, so I think what I'll do is actually just go ahead and write the first few terms of this thing out. So what I would have would be, when n is equal to 0, this will be a positive 1, and you'd have 0 plus 2, and this would turn out to be equal to 1/2. Then when n is equal to 1, you'd have a negative 1/3. Then when n is equal to 2, you would have a positive 1/4. When n is equal to 3, you would have a negative 1/5, and so on. Then a positive, and it goes off like this. Now, hopefully, when you look at this, you'll recognize, that is an alternating series, so you can possibly use the alternating series to satisfy this. So what the alternating series test says, and again, the alternating series test, we'll call it the AST, has two requirements. First of all, each term has to be smaller than the preceding term, which it is, so it passes the first part of the alternating series test. And the limit of the series has to be approaching 0, which it is. So this series passes both parts of the alternating series test, so you can use the alternating series test to show that this series is going to converge. So at the right endpoint, it converges, which means that you do include the right endpoint. So you include the endpoint on this one. So now, basically, you showed don't include the left endpoint, do include the right endpoint. So if you go back up here to the final answer, what it's going to look like would be this. You don't include this one, so you leave it open. So the interval is going to be from -1 is less than x. But you do include this, so this will change to a bracket. So this is going to be less than or equal to 1, and that's going to be the interval of convergence. So again, if you wind up with the limit being a fixed number, then you have to check for the endpoints. And as you check each point individually, if the series diverges, you don't include the endpoint. If the series converges, then you do include the endpoint.